Okay, so we have looked at the backtracking algorithm, which essentially does depth first search as we have seen, and we have also looked at consistency enforcement like algorithms like AC3, which take the problem that is given to you and pre-processes it to remove domains so that the search space will become smaller. Now, as we just discussed, we will look at an algorithm called Lookahead, which looks ahead even during search. So, before making a choice, it looks a little bit ahead to see whether something is a consequence or a undesirable consequence or not. So, that algorithm is called forward checking. One of the algorithms for Lookahead search is called forward checking, and it is as follows. The outline is same as backtracking. So, we begin like we started in backtracking, that we have the constraint network as input. We start by saying that assignment is an empty list, and now we make copies of all the domains. In backtracking, we made copy only of the first domain, and only we went to the next domain we made copies of the second domain. Now, we are making copies of all the domains, and you must also think about how many copies you need to make. But anyway, so here we have one copy, and the reason for that is that forward checking aims to delete values of future variables which are inconsistent with the value of the current variable being considered. We will see this. And if you are going to delete values of future variables, when you are looking at the trying to find a value for the current variable, if you backtrack from the current variable, then anything that you had deleted earlier must be undone essentially. So, that is why it makes all the copies to start with. Then, as in backtracking, you set that okay, I am going to look at the first variable first. So, I is equal to 1, and as long as I is between 1 and n, it goes through this while loop essentially. Now, the select value function has changed here. It is called select value forward checking, and otherwise it is similar, that you give a copy of the domain and you give the assignment which has been computed so far, the partial assignment, and of course, the constraints that have to be satisfied essentially. As before, as in backtracking, if you can't find a value, that means that select value function returns null, then you first undo the look ahead pruning done while choosing a I minus 1, and then go back to a I minus 1 by saying I is equal to I minus 1. So, that is the backtracking part here. Remove the last value you added to the assignment, because you are backtracking to the I minus, and you are going to add look for a new value for that essentially. And that is very similar to backtracking, except for this step which was not there in backtracking essentially. But this is needed because forward checking is pruning future domains. So, we want to undo that part essentially. If it has found a value AI, then like backtracking, it concatenates it to the assignment and goes on to the next variable. So, let us look at this function select value forward checking. One question that you should think about while we are doing is, because I said this at the beginning also, how many copies of domains do you need to make? It is a matter of implementation, we will not go into details, but the question is, what if forward checking backtracks 2 steps at a time? So, you are saying that I is equal to I minus 1, but if you do not, if the value that you tried for that previous variable was the last value in that domain and nothing is left, then you will have to backtrack one more step. So, do you need to undo something else? So, just think a little bit about that, and let us look at the select value forward checking function. This is similar to the select value function for backtracking, except that it is going to do some extra pruning. So, the initial part is the same, as long as the domain is not empty, the copied domain d I prime is not empty. Take the first element from the domain which is at the head of the domain, and reduce the domain by 1 by taking the tail of the domain, and then for all future variables. So, you are looking at the ith variable to assign a value, remember. Now you are saying look from I plus 1 to the last variable n and see whether everything is going to be consistent if you assign the value ai to the ith variable. How can we do that? We can say that for each b in dk prime. So, this is k for k going from I plus 1 to n, and for each value in that dk prime b, we will see whether the assignment. So, this is the original assignment that we passed to the algorithm. This is the value for the ith variable that we are considering, which is what we would return if we found it everything is okay. And this is a future value, and we are trying to see whether that future value is consistent with the assignment that we are constructing essentially. If that future value is not consistent, we delete it from its domain essentially. Remember that this k is a future variable, it is not the variable that we are trying to find a value for is the ith variable, and k goes from I plus 1 to n. So, this is deleting a value from a future variable. After having done that, after finishing this for loop, if no future variable for any k is empty, then you can go ahead and say that okay, ai is the value for the ith variable essentially. If any of them is empty, then for all the future variables that you considered, you undo the deletes that you did in those future variables essentially. So, again you should need to think a little bit about this as to whether this undoing it like this, whether it works if the algorithm had to backtrack 2 steps or 2 more steps, or do we need to specify more details. But here we have only focused on the general idea that this is how forward checking happens, that it deletes values from future variables. And if that is the case, which means that which is the else part essentially, that some domain became empty, which means you are not going to return a value for the ith variable essentially. If no domain had become empty, then this is the other return statement in the algorithm which would return the ith value. But if some domain became empty, then you would return null, and the algorithm will have to backtrack to I minus first variable and look for another value, which is like what backtracking also does. So, this kind of figure illustrates this whole process. The shaded shape that you can see, it has got these 4 values, and this is the partial assignment that has been considered so far essentially. Now, this blue node is the one that you are considering for variable 6. So, can we give this value to variable 6 essentially. The dotted nodes are that were deleted earlier by forward checking because of at some level, it could have been for level 1, level 2, it could be anywhere, because these would have been future variables at that time. So, they could have been deleted at that time essentially. The shaded values are the ones that you are deleting when you are when you are considering this value for the ith variable essentially, and these are the values that you will have to undo if you were to backtrack and say that no, I can't find a value for the 6th variable. So, this blue one is one value, if that fails you will try the next, then you will try the next, and so on. If you end up saying that there is nothing, then you must undo the whole thing. So, let us look at forward checking with an example, our favorite example of map coloring. And so, this is a problem. On the left hand side is a constraint graph which tells you which variable is related to which variable. On the right hand side is the corresponding graph graph which we will now convert to a matching diagram, but which tells you what are the values in the various variables and also in what order are you going to look at those variables. So, if the order is given here below, so G, D, B, F, E, A, C, and you can see that this value G is the first variable that we will look at essentially. Now, we will draw the matching diagram for this and see how forward checking works essentially. So, this is the matching diagram. As you can see, any color can be connected to any different color on a related variable. So, for example, E is related to B. So, you can see that this W is connected both to B and G, which means if you had a value W in E, then for B you could have B or G essentially. And likewise for R, R is also connected to both variables because that is what the map coloring problem is all about. But for the variable G, it is connected only to one variable, which is B, because you can't have a G in the other variable. So, this is the matching diagram that we have discussed earlier, and now we will watch the progress of forward checking on this problem essentially. So, the order is, as you can see on the right, the G variable G is the first one, and we will pick the first available value for G, and that value is W essentially. So, what I have shown in yellow are, so G, as you can see on the top left, is related to E and to F, and if you were to choose W for G or white, let us say W is for white for G, then you cannot have white for E and for F, and this yellow nodes show that if you are going to select this the white for G or W for G, you will have to delete it from this thing. So, those two nodes have gone, as you can see, one was in F, one was in E essentially. Forward checking does only this, it looks at related variables and sees if you can prune them essentially. Later on we will see a quick glimpse at an algorithm which does more reasoning even while assigning a value. So, forward checking is done with a value of 1 for G, so which we have shown in gray, and it goes to the second variable, which is D, because that is the order in which we are processing them, and it considers the first value for G. Now, you can see that choosing this G does not affect its related variables, which are C and F, because C has got an R red and C has got a red and a blue, and F has only got a red. So, nothing will happen. So, that goes forward. The third variable is B here, and we look at the first value for B. B, as you can see on the top right, is related to three variables E, A and C, out of which A and C have another B, which means those things which are shown in yellow will get deleted at this stage itself. So, we are done with the third variable, which is B equal to B. Then we come to the fourth variable, which is here, and we choose the one value which is R essentially. When it chooses this value R, it will be forced to delete this R from C essentially. Why? Because as you can see on the top left, F is related to the variable C, variable F is related to the variable C. Variable C had the value of R, and because you are choosing R for F, you have to delete it from there essentially. Not only that, it does not notice that the edges AC and CF. What are the edges AC and CF? AC is this one and CF is here. Have become arc inconsistent because it is only looking at a future variable which is C, and it is going to delete that value from there essentially. But at this point the domain of C will become empty. right. So, it notices that the domain of C has become empty, and so it has to backtrack. Where can it backtrack? From fourth variable, it will go to the third variable, and it will say, okay, let me consider the second value for G, and it does the same process. So, when it is considering the second value from G, you can see that it will have to delete G from variable E, which is related to that, which is not only related to that, but which is also in the future. So, when you are looking at the third variable, you will only look at future variables essentially, and so G happens to be one of them. Then it comes back and tries a value for R. See, now because we moved from B to G, this value is allowed for C, because now we can say that C can get a value of blue or B, because the third variable has the different value essentially. So, now we try this value of R for F, and at this point we will delete R from C, but that does not make that domain empty essentially. So, this would go through successfully. Then we will try a value for E and the R value, at which point we will delete the value R from A, and we will reach this stage essentially. But at this stage, forward checking does not see that these two have become inconsistent, that they are not R consistent with respect to each other, that you can choose B for one, but you cannot choose the same B for another. Forward checking is not able to do that, because when it was looking at the fifth variable, it was only looking at connected variables. So, what are the connected variables? There is only one connected variable in the future, the others are there, but they are in the past, and forward checking only removed that value from the connected variable in the future, which is R. It does not look at the relation between A and C at this stage essentially. There are other algorithms which do more consistency propagation when they are looking at the future, and we will see a very quick example here. So, forward checking does not see that A and C are that AC, the algorithm, that variable A is not R consistent with C, and plots on to the value of A. It will give a value of B to A, and when it does that, this value from 7 will get deleted, and it will notice that that is become as empty. So, it will backtrack. Where can it backtrack to? It will have to backtrack. So, it does not assign a value from A, and it will have to backtrack from here essentially. So, whatever the values were, it will go, maybe for variable D, it will try something or something like that and proceed in this fashion. So, this I hope gives you a flavor of the algorithm forward checking, and what it does is that it looks at every future variable for the variable being considered and sees whether any value should be deleted from that future variable. So, it is as simple as that. It does the least amount of work in looking ahead essentially. So, there are other algorithms which do more work. So, they are called partial look ahead. Partial look ahead says that if you are looking at variable I and you are pruning a value from a future variable j, then because of that will you have to prune a value from a future value k essentially. So, that is extra work. Forward checking is only looking at the current variable and what it is connected to. Partial look ahead looks one step further ahead or more steps further ahead. Then there is full look ahead, which basically says that see consistency in both directions. Forward checking and partial look ahead are looking at consistency only in the forward direction. And then there is something called R consistency look ahead, and what that does is that the last one, which is R consistency, implements full R consistency between the future variables. So, it will try to see whether all the future variables can be made fully R consistent, and we take a quick look at this before ending up our discussion on constraints essentially. So, the same problem that we have and the same algorithm which is now we are looking at R consistency look ahead. So, throughout the next few figures that we will see, we will only look at the fact that it is looking at assigning w to the first variable g, and what we are showing in step by step is the propagation that happens, which tells you as to which will have to be removed essentially. So, as you can see, because from w you will have to from w you have to check whether this variable is consistent with this variable, and you will end up removing r essentially, which is what forward checking was not doing essentially. W has removed w from here, but that is a different matter. So, remove w from f and e as we had said here, remove r from c from here because it is not consistent with f. After you have removed this w from here, then we find that c, which has an r, is not consistent with f, because if you choose a value of r for c, you will not get a value for f. So, we are doing full r consistency. So, we are going to be looking at consistency in both directions for all future variables. So, r will go from c, and then we are still looking at this thing, that can we give a value w to g. Next, you remove b from a, b and d. Why? Because they are related to each other, and this is, those are not are consistent with respect to, those values are not are consistent with respect to this. So, you remove, you prune the variables a, b and d, that is what we have written here. Next, you remove r from e because it is not r consistent with respect to a, and you remove g from e because it is not r consistent with respect to b essentially. So, both will go essentially. At this point, and this algorithm AC look ahead, R consistency look ahead, is only still considering whether you should give a value of w to g. And while doing this future R consistency, future variables R consistency, it has noticed that they are not R consistent, that the value of a variable has become variable E, the domain has become empty. So, even at this stage, it abandons this value w and goes to the next value r essentially. So, this is just to show how much more work this is doing in consistency enforcement, even for looking at the first variable. It does not have to do more search. So, this kind of exemplifies the fact that the more consistency enforcement you do, the more propagation you do, the less will have to be the search. So, it has only started by looking at the value w for g, and it has abandoned it even at that stage. So, we do not have time to go into more details. Just a passing mention on look back search. So, look ahead search tries to prune future variables, and as we saw, there were 4 algorithms: forward checking, partial look ahead, full look ahead and AC look ahead, which did increasing amount of work. But what about looking back? Algorithm backtracking does what is we call as chronological backtracking. This means that on reaching a dead end, which is some variable, it looks for another value for the previous variable, and this is chronological, systematic in some sense. Now, can one choose a variable that you want to undo in a more intelligent manner? And we had in the passing mentioned that there is something called dependency directed backtracking, but we do not have time to go into that. So, these methods are called jump back methods, which means they jump back to some previous variable, not the last one that you were looking at it, and they try to identify which is a culprit variable that you need to jump back to that has caused the current dead end essentially. So, these are called look back search methods. They investigate different ways of identifying the culprit. Some of them look at it based on graph topology as to which variables are connected to which variables, and therefore, how did the inconsistency arise. Some look at values that cause the conflict, that these values what cause the conflict, but we will unfortunately have to leave it there essentially, but you must be aware that that is another aspect of constraint processing, is that you do consistency enforcement, you do look ahead search, and you also do look back search methods, but we do not have time to look at that. So, to end, uh, we had said a couple of times that there are people, in particular Freuder, who works at the University of Cork, who is also known as father of constraint satisfaction. Uh, the University of Cork has a full center devoted to constraint. It is called Cork Constraint Center, and Freuder has said in his paper, which is given below, uh, that the holy grail of computer science is to solve the constraint satisfaction problem, or work on constraint processing. And he says this is consistent with this notion of artificial intelligence, that the user states the problem and the computer solves it essentially. And what we have been trying to emphasize is the fact that constraint processing subsumes both search and knowledge representation and reasoning, which we consider to be the core of problem solving. So, it offers a unified framework in which search and reasoning can be combined, that is the important part. And we have also observed somewhat casually, but we have made this observation that the more the reasoning, the less will be the search. So, there is always a trade off between the two. Then we saw that look ahead methods integrate reasoning with search, look back methods also integrate reasoning with search, though we have not seen the details. Look back methods also exploit something called memorization, or some people call it memorization, which says that if something failed, then remember that it failed and do not try it again essentially. So, with that we come to the end of this session and the end of this course on artificial intelligence, search methods for problem solving. I hope you enjoyed the course, and I hope you will benefit from it essentially. Thank you.